Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Keith Olive, who is a theoretical physicist and director of the William Fine Theoretical Physics Institute at the University of Minnesota, specializing in particle physics and cosmology. His main topics of research are Big Bang nucleosynthesis, particle dark matter, Big Bang baryogenesis, and inflation. Welcome, Keith.
Hi.
I want to start with, sort of laying out the chronology of the universe. We know that something happened 13.8 billion years ago. We don't know exactly what that is, but since then, we have a reasonably good understanding of how the universe evolved, right? And so there are certain timing and regions of this timeline that has special characteristics, special interesting things that happened during that time. So do you want to sort of lay out the chronology a bit?
Sure, I can do that. As you said, the very beginning is not very clear. That's not very well understood. We call it the Big Bang. What exactly is the Big Bang? We don't know. And the main problem is that, the universe as a whole is run by gravity. And as we go back in time to the very first moment, gravity should be very strong. And for that, you would really need to have a quantum theory of gravity, which we don't have. The closest thing there is a theory called string theory, which should be a unification of all the fundamental forces, which include gravity. But that theory is not complete. And so we still have a question mark as to exactly what happened in the first instant. However...
So Keith, in the first instant, the four fundamental forces, we believe should be all unified, right? So gravity, strong and weak forces, and electromagnetism.
Right. As I said, that's not fully understood. There is a theory that unifies three of them. It's called a grand unified theory, that all three except for gravity. In principle, string theory should be a comprehensive theory that encompasses all four interactions and perhaps others. But it's also possible that there was no exact beginning in that sense. So in most cosmological paradigms now, there's a theory called inflation. And that was also extremely early on, a period where the universe started to expand extremely rapidly. It could also be that is, in some sense, the state of the universe on extremely large scales, that it is always in that state where it's expanding very rapidly. We say it's expanding exponentially. And that occasionally out pops from that a region of space and time which is a little bit more like the one that we live in. That's
Yeah.
a theory called eternal inflation, and most inflationary theories, in fact, are in some sense eternally inflating, and that would avoid this idea that you ever had an initial singularity,
Mm.
or the Big Bang is, sort of the classic notion of that.
So in that context, we could have sort of an inflationary epochs like that in our current universe that could sort of start another universe from within.
Yeah, although you have to be a little bit careful because the distance scales that we're talking about on which this is happening are so immense,
Yeah.
much, much farther than, we talk about an edge of our universe. By that we mean, you mentioned 13.8 billion years, which is the current estimate of the age of the universe. And
Yeah.
so you can imagine going out to a distance at which light traveled that over that period of time. That would be sort of like our visible edge of the universe. We call it the horizon, just like
Yeah.
looking out over the ocean. You can only see so far because afterwards the Earth turns away and you can't see past that. So there's a horizon in the universe. We can only see out so far. Doesn't mean the universe ends there. The universe might go on forever. And out distances much, much larger than that horizon in the universe might be still in this inflationary state. And it could pop out some other, I put in quotes, universe. But in some sense, that's irrelevant because that will be moving away from us. And your listeners might be a little bit upset with what I'm going to say, but it's going to be moving away from us faster than the speed of light. It
Right.
doesn't
Right.
violate anything because that's all within the context of general relativity. There will never be a signal. We can never get a signal from that other universe.
Yeah.
But it might still be there. That gets us out of the realm of physics a bit because that's more, I would call it metaphysics because it's completely untestable. It might be,
Untestable. So it's going to be all speculation.
it could be
That.
speculation.
Yeah. Yeah.
It could be true. We will never know because we can't get a signal from that.
Right.
It's beyond our horizon, and it will always be beyond our horizon. So, um, uh, as I say, it's a little bit metaphysical. It's sort of fun to think about, but the part that is a little bit more real is the inflationary patch, I could call it, that we grew
Yeah.
out of, and because
And that's a very short. So I just want to give a scale of that. So the inflation that we're talking about in the universe that we know, we're talking about 10 to the power minus 35 second, right? So we're talking about a very very small period of time
that's right.
right after the origin,
Yeah.
right?
So again, you have to be a little bit careful about that bit about the origin. It is the time scale that we're associating with the after inflation. So again, the notion of time before that can be a little bit sketchy or a little bit more complex. But once we get out of this period of inflation, then we put a timestamp, and 10 to the minus 35 is seconds, is sort of
Yeah.
the standard, generic number for that. And so, yes, in that sense, it's a very short period of time, but leads to very distinct observational effects, and some of which have been tested already.
Right, right. And so right after that is what they call the age of leptons. So leptons are things like electrons, right? Um,
Yeah, I don't know if I would really call it the age of leptons per se. It's more usually it would be called, right after inflation, it would be called the radiation epoch. The universe was extremely hot,
yeah,
and so it was populated by all sorts of particles. Leptons are a class of particles, which, as you said, includes electrons. It includes neutrinos and their copies, which we call other generations. So there's the electron and its neutrino is one generation,
yeah,
and then there are two more. The charged one is called mu, and the third one would be called tau. But there are also all the quarks that are present in the universe, and all of the other particles, photons and other carriers of forces and the Higgs particle. Everything was present. It was all there at that
Yeah.
point.
Okay. And there are some ideas around that time frame. So tell me if I get this right. So, 10 raised to minus 35 to 10 raised to minus 6 seconds or so.
Okay.
That is the time frame we're looking at.
Right. That's
Okay. And so this idea of leptogenesis, essentially, how did it kind of evolve? And there are some sort of mysteries that we'll talk about at a later time in terms of it's we get matter but not antimatter, and other aspects of the universe that we witness appear sort of strange. But in this early time frame, there are some ideas that might fit with what we observe, right?
sure. Let me maybe put it into context, because
Okay.
leptogenesis is a particular model or theory of baryogenesis.
Okay.
They're very much intertwined. All this started in the late 70s. So and let me say what happened sort of in the mid 70s, as more and more became understood about the unification of the forces. So we're talking about electromagnetism, the weak nuclear force, and also the strong nuclear force. In the late 60s, the electromagnetism and the weak force were understood in some unified sense, not truly unified. And then in the mid 70s, there were some ideas put forth about what I said was called grand unification, which unifies all three forces, electromagnetic, the weak, and the strong force. That's called, and as I said, that's called grand unification. Now,
Yeah.
In grand unification, there are additional, if you want, forces. There are additional particles that mediate forces, and they don't respect some symmetries that we seem to observe today. And that one symmetry is called baryon number conservation. So what's baryon number? First of all, the baryon, that's the baryosynthesis, is where that number is the generation of a baryon number. And baryons is a class of particles. You mentioned leptons before. Baryons is another one. Protons and neutrons, for example, are baryons. They're particles made of three quarks. And so quark is another fundamental particle like the electron. The proton is not a fundamental particle. And
so you have three quarks that make up a proton and a neutron?
Yes, not the same quarks. So in a proton, there would be, there are 6 quarks altogether that we know in nature. They're called up and down, charm and strange, and top and bottom. And,
right.
And so it's, again, the 3 families, just like the leptons, the electron, mu, and tau, each with their neutrinos. So they come 3 of them, and they're pairs of 3. So there are 6 each. On top of that, the quarks have another property which we call color. So there are, of each of these, like the up quark, there are 3 different varieties of that. But a proton would be 2 ups and a down, and a neutron would be 1 up and 2 downs. So different combinations of these quarks will lead to different particles, which have all been produced since the 1950s in accelerators. So if baryon number is conserved, it would mean that the lightest baryon would have to be stable, because it couldn't decay into anything. Most particles are not stable. Even the neutron is by itself is not stable. It has a lifetime of about 10 minutes. And it'll decay into a proton along with an electron and a neutrino. It's a weak decay. But the proton then would become stable, because it has nothing it can decay to. And that's a consequence of baryon number conservation. If baryon number is conserved, then in effect, unless the universe started out with a net baryon number, there would be no way to produce it.
So Keith, more simplistically, then, if I understand this correctly, the number of protons and the number of neutrons that aggregate sum should stay the same.
That's right. That's right.
Okay.
So the total baryon number, if you have a collection of neutrons and protons, the total baryon number of that system would be the sum of the number of neutrons and the number of protons. And you can convert between them, but that sum has to stay the same. And that's baryon number conservation. Right. Now, these grand unified theories don't respect baryon number, and so they can change the baryon number. In fact, the proton can decay. And that led to a whole slew of experiments that started in the late 70s looking for proton decay. Now, that lifetime is very, very long, much, much longer than the age of the universe. The limits on the lifetime now are on the order of 10 to the 33 years. The universe itself is only 10 to the 10 years, right? So this is much, much longer. Of course, you would never find it by looking at one proton. You have to gather tons and tons of protons and look for one of them out of everything that you're observing to decay. So baryogenesis was originally a theory that came out of grand unification, where you try and produce the baryon asymmetry of the universe. And more simply put, the matter-antimatter asymmetry of the universe. So all particles have their antiparticles. The electron has a positron, which instead of being negatively charged is positively charged. And the proton has an antiparticle, which is called an antiproton. And there's an antineutron. These have all been discovered. This is not speculation. This is all well determined science.
They all exist,
For a long time now. I don't have the dates in my head, but nearly 100 years, not quite, but for the discovery of antimatter.
But the puzzle is we would have expected sort of an equal number of protons and antiprotons in that soup, in that early soup, right? In which case, if they were exactly equal, they would have negated.
They would have negated each other, and by that they would have annihilated with each other in the universe to such an extent that there would be very, very little matter left in the universe today. There's no possibility of making a star or a galaxy or anything else. It would be orders of magnitude off. So something had to happen, and what that something was actually laid out by the Russian physicist Andrei Sakharov in 1967. He said you need three conditions, and between a universe that's expanding and grand unified theories, all three of those ingredients were present. And so there are some very simple and elegant ways of generating a baryon asymmetry, of generating a net baryon number in the universe, which would lead to only matter or only antimatter. And of course, whatever's left over is the one we call matter. A priori, it doesn't make any difference.
Is there, Keith? Just a quick question: is there any possibility that there is a side of the universe that we can really probe that is made of antimatter? The reason we are not seeing it is because
it's a good question. I mean, you can start by asking. We know the Earth is not made of antimatter. I mean, that's because we've defined it that way. Also, there's not like an antimatter mine, right? You can't go somewhere and start digging and find some cave filled of antimatter, right? Because it would have just eaten up the Earth. The moon is not antimatter. Neil Armstrong showed us that. The sun is not antimatter because lots of particles come off the sun in the solar wind. This whole solar system's not antimatter. In fact, you really know the whole galaxy is not antimatter because we get all sorts of particles from the galaxy in the form of cosmic rays. So you can then say, what about the next galaxy? Could that just be an antimatter galaxy? Again, the answer is almost certainly. I mean, eventually you go far enough, we become a little bit less certain, but we're pretty certain there's really no antimatter in the universe. It's never been seen in the cosmic rays where you actually find as a primary particle something like anti-helium, right, which would be very hard to
Mm.
produce. It's extremely hard to produce. And so it is possible in a collision to make well, certainly antiprotons are made in collisions all the time, but even things like
Yeah.
deuterium, which is the smallest nuclei with just a neutron and a proton bound together, or anti-helium,
Mm.
you can make them, but they're not found as really as primary particles.
Okay. So we are pretty confident the current universe does not have any antimatter particles. And so the puzzle is if you started with, sort of equal numbers, you cannot get
Unless
here,
you violate
which would,
baryon number
yeah,
conservation.
uh, unless you violate something. Okay. So that is the saga of
That's right.
conditions,
That's right.
right?
Well, you have to violate baryon number is one of the conditions. You have to do it in a
Okay.
way which sort of prefers one over the other. It's more technically,
Mm.
it's called C and CP violation, which is charge symmetry and charge and parity symmetries. Um, and the other is that you have to do it out of equilibrium, because if you do it in equilibrium, both forward and backward reactions will be equal, and any baryon number you make will just be erased by the backward reaction. So the fact that the universe
Mm.
expands gives you a chance of doing something out of equilibrium. And the simplest mechanism that was really first proposed, I think it was 1978 or 79. Really, it's time when I was just starting out my research career. It was one of
Yeah.
the things that fascinated me is that some of the particles associated with grand unification, when they decay into slightly unequal amounts of baryons and antibaryons. Uh,
Mm.
and if that happens out of equilibrium, that will lead to a net excess of one over the other. And so it was a very natural
Right.
thing that you start out the universe with all of these particles. It's very, very hot. And then as the universe cools, these particles start decaying, but they decay in a somewhat biased way. And that bias is coming
Mm.
from this C and CP violation, which is also in other systems is something that's observed. It was discovered in the 60s for different particle systems. So this seemed to be a very natural way of generating an asymmetry. Um, Let me shift now to leptogenesis because in some ways it's
Yeah.
very, very similar. So leptogenesis is associated, as you mentioned earlier, with neutrinos. And I said that there were three neutrinos and they mix with each other, meaning they're not the neutrino that's associated with the electron and the one that's associated with the muon. They're not really distinct states. Quantum mechanically,
Mm.
they they can evolve from one to the other. And
Yeah.
to do that, they have to have a mass. And this is something,
Okay.
and it's now well understood that they do oscillate, which is what's observed. Neutrinos coming from the sun oscillate. Neutrinos coming made in the atmosphere from cosmic rays are seen to oscillate. So this is something that's fairly well understood now. It's certainly observed and in that sense. Um,
So oscillate meaning they start as one variety, and by the time they reach us, it's a
That's
different
right.
variety
You
altogether.
can make an electron.
Okay.
So the sun might make an electron neutrino because those are the
Mm.
interactions that you would have in the sun. But when they get here, they're not all electron neutrinos anymore. Some of them have become muon neutrinos or tau neutrinos. The ones
Mm.
made in the atmosphere are largely muon neutrinos. But when we see them in the detectors, some of those muon neutrinos will have turned into electron neutrinos.
Is that totally random, or is there
No,
any
there's
patterns
patterns
to
to it. I
it?
mean, it's again, it's understood. I mean, it has to
Yeah.
do uh, with the relative differences in masses between them,
Mm.
but they have to have mass. The original electroweak theory, the simplest thing was to just keep neutrinos as massless particles, but um, because there was no evidence for it at the time. Now we know neutrinos have mass. And the question is, how do they get their mass? Do they get their mass in the same way that, say, the electron gets its mass, which is through interactions with the Higgs boson, which is why when the Higgs boson was discovered, it was such a big deal? Or is it a little bit different? And the probably the most common theory behind neutrino masses, and it's still a theory, the exact mechanism for neutrino masses is not known and might not be known in our lifetimes, and I'll explain why in a minute. Electrons get their mass through the interaction with the Higgs in a very simple way. There are, in some sense, two kinds of electrons, a left-handed electron and a right-handed electron. One has weak interactions, the other doesn't. The left one does, the right one doesn't. They both have electromagnetic interactions. And the question is that the same? It could be the same way for neutrinos. You just have a left neutrino and a right-handed neutrino. They both, in effect, have the same mass. They interact with the Higgs, and that's the end of the story. It could also be that the right-handed neutrino is extremely heavy and gets a different kind of mass. Because it's neutral and it actually doesn't have any other interactions, it could have a mass, a right-handed neutrino mass, just in and of itself. And if it's really heavy, then when you work out the mass states, there will be some mixing between the right and left neutrino, and you will get still two different masses. The right-handed neutrino mass will primarily still be really heavy. By really heavy, I mean maybe 1 trillion times heavier than the proton.
So when you say different kind of mass, almost everything that has a mass really gets it through the Higgs
That's
field, right? And so when you say different kind of mass, this is one instance where the mass is
independently. That's right. It would be a mass independent of the Higgs, and that would only be for the right-handed part. But because the right-handed and left-handed part mix, the left-handed part, or the state that we see today as a neutrino, has some little piece of that right-handed part in it, and its mass is going to be something like a regular particle mass, but actually squared, divided by this very heavy mass. So all of a sudden, you've got a normal mass times a ratio of a normal mass over a really heavy mass, and that makes the neutrino we see to be extremely light. And that's what we see. The neutrinos' masses are all much, much lighter than any other particle mass that we know about. So that's one reason, that's one explanation for why neutrino masses are so light. It's called the seesaw mechanism. If you think about it, you're starting with something normal and something really heavy, and the really heavy thing makes the normal one really light. That's it's called the seesaw mechanism, and that's sort of the analogy. Now, what is leptogenesis? So leptogenesis involves sort of this decay of this very right-handed neutrino. If this very heavy thing was present in the universe, it will decay, and if it's actually its mass now violates lepton number. So I said there was baryon number conservation. There's also lepton number conservation as well. So the lightest lepton, which would be then a neutrino, would have to be stable as well, because there would be no other lepton for it to decay into. In a grand unified theory, the simplest grand unified theory, the difference between baryon and lepton number is conserved, B minus L. So the total B minus L number of the universe should be 0 in the simplest grand unified theory.
So B minus L meaning that the baryon number minus the lepton.
Now, this heavy mass that I mentioned violates lepton number automatically, and but it doesn't violate any other principle, and what I mean by it doesn't violate any other symmetry, and the ones that we really hold sacred are called gauge symmetries, and they're the ones that control the fundamental interactions. But this neutrino mass doesn't violate any of those, but it does violate lepton number. So now, when this heavy neutrino decays, it can generate a little bit. Okay. Then there are other processes in the electroweak theory that can shuffle lepton number into baryon number. And that's what leptogenesis is all about. The leptogenesis is generating the lepton asymmetry through these very heavy neutrino decays. And so now once you have that lepton asymmetry, so long as you do this while the electroweak theory is still a good symmetry, so now we're talking about times before 10 to the minus 10 seconds, some of that lepton asymmetry will get converted to a baryon asymmetry, and therefore we end up with a matter asymmetry, a matter over antimatter asymmetry. So that's the basis of the leptogenesis. It's very similar to baryogenesis, but converts a lepton asymmetry into a baryon asymmetry.
Okay, so let me see if I understand this, Keith. So the heavy right-handed neutrinos, which sort of has a different mechanism for its mass, when it decays into leptons that could then be converted.
That's right.
Into
so it
baryons?
Decays more into leptons than anti-leptons, say.
More into leptons. So it's a preference of decaying into let's say an electron, which is then, or it could be maybe it has a preference to decay into anti-lepton, like a positron or something, and then that get converted into a proton.
So no,
what exactly happens
it
there?
would have a preference of getting converted into leptons over anti-leptons. So you're right, it would be neutrinos and electrons over positrons and anti-neutrinos. It would rather have an excess of lepton asymmetry. And that would get pushed into a baryon asymmetry. So again, that would get pushed into, because of other conservation, for example, like B minus L. If B minus L, everything is then, there's a whole system that all this gets done in equilibrium, and it all depends on, just like a regular chemical reaction, there's all kinds of chemical potentials that you have to worry, but some fraction of that lepton asymmetry gets put into a baryon asymmetry, and you end up with more quarks than you do anti-quarks, and that will lead to more protons than antiprotons. And then as the universe continues to evolve, all that antimatter annihilates, and what you're left over, what we're made of, is the leftover.
Right. And so again, this is really early in the universe's
before
evolution.
10 to the minus 10, before the electroweak symmetry gets disturbed.
At very high temperatures, if I don't know if I understand this, Keith, at that temperature, the Higgs field cannot be more than zero?
You mean the value of the Higgs field? Oh, yeah, in a sense, yeah. You're talking about the period where the electroweak symmetry is not broken, so the average value of the Higgs field would be zero.
Would be zero. So the only thing that could have mass during that time is this heavy right-handed neutrinos.
Yeah, in a sense, there are also temperature-dependent masses. So the idea of mass is is really should be a final thing that you're asking about the property of a particle.
Okay, because you have energy, and energy is basically mass.
They're in a thermal bath, and so there are thermal contributions to their masses as well.
Right. So if this were true, we have a possible answer to the asymmetry that we see between matter and antimatter. And so I understand that the Fermi lab is doing some sort of an experiment on the neutrino to prove or disprove this.
You have to be a little bit careful.
Okay.
Some of that is a little bit press, and what they're doing is great stuff. I don't criticize what they're doing, but a little bit is spin because
Yeah.
the right-handed neutrino, if this theory, and the theory makes sense, it's I'm not sure all your listeners will find it simple, but to us it's actually quite simple. Um, but the
Yeah.
right-handed neutrino might be, as I said, extremely heavy, and Fermilab is not going to see the right-handed neutrino. What Fermilab is doing is really trying to understand, as I mentioned before, there's this breakdown of some symmetries called C and CP. So they're really looking for the
Yeah.
CP violation in the neutrino sector. We expect that to be there because there's CP violation in the quark sector. That's well established. And we're trying to well establish to put it on the same sort of basis to see the CP violation in the lepton sector as it is in the quark sector. So that's really what Fermilab is doing. That may or may not be related to the CP violation in these heavy neutrino decays. That's where I get a little bit nervous about that direct connection. But the
Okay.
neutrinos, the neutrino mixing and the neutrino CP violation is still part of the same big picture.
Okay. Okay. And so once we get to a point that we have more quarks than anti-quarks, then the nucleosynthesis part of it, there are some, and essentially getting to lighter elements like hydrogen and helium.
Yeah,
There are some
so
puzzles there too,
just
right?
to get us to that time period,
Yeah.
I said 10 to the minus 10 seconds, which is only a tenth of a nanosecond. It's short, but not that short.
Yeah.
That's when the electroweak symmetry breaks down. Then you go, a short time later, at about 10 to the minus 5, 10 to the minus 6 seconds, is when you have the period where now the free quarks are no longer free. They now start combining into neutrons and protons. At that time, they'll probably still be making some other particles called pions. They're mesons. They're also originally thought to be carriers of the strong force at much lower energies, and they were also observed in cosmic rays as well. Their decay products and things.
Yeah.
So so now you're at a little bit later time. Now you have neutrons and protons, but the universe is still too hot, and so it has. Well,
Still
we're still less than
a
a
second
second
old.
old, and so once we get to about a second and a little bit later, within the first, let's say minute or so, then what can start to happen is that the neutrons and protons can start combining to make, as I mentioned, the first non-trivial isotope, which would be deuterium, which is the bound state of a neutron and a proton. At higher temperatures, there's a whole lot of photons or just radiation, light, that would break up the deuterium. So you could make deuterium earlier, but there's all these high energy photons would smash into the deuterium and break them back up into neutrons and protons.
This is the deuterium nucleus,
that's
right?
It's heavy hydrogen. Right?
Yeah.
It's chemically it's like hydrogen, but its mass is almost about double. I should say also that the baryon asymmetry that we got left over with, the matter asymmetry, is very small, right? We say it's very small because the number of protons, say, compared to the number of photons, the particles of light, is only about 1 in 10 to the 10, so 1 in 10 billion. So there's a lot more light out there than there are.
So that slight asymmetry that we saw in the baryon arena, it is really, really small. So whatever was left is minute.
That's right.
Compared
It's
to
very
how many
small
photons are there.
leftover, if you want. But that leftover was enough to make all the galaxies and clusters of galaxies and stars and everything that we're made of. So there's a lot of photons out there. So you have to actually wait until the universe cools so that the energy in the photons can't break up the deuterium. And once that starts, and as I said, that happens when the temperatures are actually similar to what's going on in the center of the sun. It's about 1 billion degrees or so. The lifetime of the universe now is about a minute. It's within the first couple of minutes. And the first thing you produce is deuterium, and then you get a series of chain reactions, nuclear reactions that go forth. You start making deuterium. You'll make some tritium, which isn't stable. That's even heavier hydrogen. It's got two neutrons and a proton. You'll make helium-3 and helium-4, and then you'll make some lithium. There's 2 isotopes that are stable, lithium-6 and 7. And by that, this all takes a little bit of time. And by time you get up to lithium, then the universe is always cooling as it's expanding. Time is going forward. It's cooling. Now there's less energy. The density is too small, and the nuclear reactions basically peter out, and that's it. You're done. You've got, but what you've mainly produced is helium-4. In fact, you've taken about 25% of the mass in matter or baryons and made it into helium-4. Well, everything else is hydrogen, right?
Too,
so
right?
There's a tiny bit of lithium. That's also now 1 part in 10 to the 10 of the hydrogen. But and deuterium and helium-3 is 1 part in 100,000. So basically, you've got 25% of the mass in helium, and then the other 75% is hydrogen.
Yeah, so I guess that's why I get confused. So we are still talking about nucleus.
We're certainly not talking about atoms.
About
Everything is complete. All the electrons are out there floating around, but everything is ionized. So you've got bare protons and bare helium nuclei. There's no atomic states yet. That happens much later.
Right. And so as we go forward, again, this process continues. It expands, it cools, and then electrons come together to marry with the hydrogen and the helium.
Yeah, and that happens
nuclei,
about 100,000 years
atoms.
later. Yeah, so it's a big, and again, the reason is that you have to wait until the universe cools so that all those photons don't ionize the atoms. Right, so you have to let the atoms you have to let the nuclei capture the electrons, but if it's too hot, then some photon will come and blast the electron off again. So you have to wait until the universe cools, and that's very late. If I can inject a note of history here, the theory of nucleosynthesis or Big Bang nucleosynthesis originated actually in the late 40s, and by 2 physicists, Alpher and Herman. They were working with the senior physicist there was George Gamow, who is thought to be the father of modern day Big Bang cosmology. In fact, there was another competing theory, which was called the steady state theory of the universe, sort of by. No, that's different. Einstein's was the Einstein static universe. That was different. That was the one he didn't want to be expanding at all. The steady state universe is expanding. It's actually more like inflation, but they basically wanted the universe to always look the same as it does today. It's expanding, but it's always expanding in the same way and never really changing. And Fred Hoyle, who was one of the main proponents, he actually named the Big Bang theory, but he did it to be derogatory. He thought, if I call it something silly, nobody will believe it. And so he named it that silly Big Bang theory of Gamow. But Gamow's student and one of his researchers, Alpher and Herman, while working on nucleosynthesis. So they knew that the universe had to be very hot, that it was expanding. They wanted conditions like inside the sun where you can make heavy. Actually, they were trying to make all the elements. They wanted carbon. They wanted the whole table of elements to be made in the early universe, and that just didn't work. But they noticed, they said, oh, by the way, with all this radiation in the early universe, that should be left over today. And they actually predicted in 1947 or 48, I think it was 48, that there should be some remnant of this, and it would today have a temperature between 1 degree and 5 degrees Kelvin. And that was sort of just left, okay, what are you going to do with that, right? And in the 40s, there was no technology to discover it. But in 1964, Penzias and Wilson, working at Bell Laboratories in New Jersey, found that, oh my gosh, we got some noise in this antenna that we're building. And over in Princeton, Dickey, Peebles, Roland Wilkinson said, you just discovered the Big Bang. And this leftover radiation, which we now know is 2.7 degrees to extremely high accuracy. It's 2.7255, right? It's really cosmic microwave background
So this is what's called
radiation.
the
And it was predicted
microwave
by Alpher and Herman to be between 1 and 5, so they got it right. And that was because they were doing the work on Big Bang nucleosynthesis.
Right. So this is sort of the first light when photons could sort of get out. So
once you did cool down, so now again we're 100,000 years past the Big Bang. We already talked about what that meant, but and then then light becomes free. So before you had a plasma, right? You have all these charged particles, charged nuclei, charged electrons. So the photons would be bouncing around all the time. But as soon as you make the neutral atoms, then these photons all of a sudden are free. They don't see charged particles in it. They see a bunch of neutral atoms, and they stream out, and they keep going until some of them hit our detectors, and that's what we see as the microwave background.
And they have been traveling a long time. They basically
the universe keeps cooling. So when they were emitted, the temperature was about 1,000 degrees or so. And the universe keeps expanding, they keep cooling. And so by the time they get to us today, as I said, it's 100,000 years later, their temperature is cooled by a factor of about 1,000. And we see them as 2.7 degrees today.
Yeah, this seems like a very consistent story, Keith. I wondered, is there anything in this understanding that gives us any clues about the dark matter?
So it is a very consistent picture. There is, if you want, we have now over the last 20 years or so developed what's called the standard model of cosmology. We call it lambda CDM. CDM stands for cold dark matter, which is what you just mentioned. And the lambda corresponds to, it's called lambda because it's referring to the cosmological constant that Einstein actually introduced for this Einstein static universe. He found that the universe was expanding or contracting, and he didn't like that. And he had his own notion of the universe at the time, which should be just sitting still. And so he said, oh, but I can introduce a constant and I can stop the expansion. And then he actually could have known about Hubble's work at the time. But once he realized, well, the universe is expanding, he goes, oh my God, what did I add that constant for? I didn't need that, right? But it seems, though, from looking at the universe today, everything fits extremely well, unbelievably well almost, if you do have a tiny constant. Whether it's exactly constant or it's changing, nobody knows, but it seems to be pretty constant with extremely small value. That value we don't understand. That is a big puzzle as to why this dark energy has its particular value, or if it's a cosmological constant, why it has that particular value. That's an outstanding problem, and that there has to be a lot more matter than is just in protons and neutrons, and that's the dark matter. But
Right.
with dark matter and this cosmological constant, it's amazing how much can be explained, and primarily through the microwave background. What we see, the details that are seen in the microwave background. Um, there are so many things that get fit by so few parameters. It's astounding. Uh,
But from a particle physics perspective, we still don't
that's
have
certainly
a
true.
good
We
handle on the
don't know
dark
what it
matter,
is. There
right?
are a lot of ideas.
Yeah.
Some of the better ideas are not being found. I mean, there was a lot of anticipation with the LHC, which did find the Higgs boson, but did not find anything else so far.
Mm.
And a lot of people thought there should be all sorts of new stuff coming out of the LHC, lots of new particles, and some of which could be associated with dark matter. And that's been a big disappointment.
Is there anything to this
Well,
idea of the primordial
it's
black
possible.
holes as a
I
candidate?
mean, personally, I think it's simpler to explain it in terms of a new particle, um, because we understand how you would
Yeah.
make new particles in the early universe after inflation or just thermally. There are all sorts of ways you could do it, but they're very well understood. Now, making black holes, you have to make them the right size.
Mm.
You have to understand how they're made. It's possible, but it's, I think, much more speculative. And then and how you get the right number. The
Okay.
nice thing
Okay.
about the particle dark matter, at least some of the ideas which, as I say, so far have not come to fruition, is that how much of it gets left over seem to be very naturally the right amount that would account for the dark matter. But that's still to be proven. It's still to
Mm.
be. There's a lot of experiments looking for dark matter. Sort of direct, what we call direct detection experiments. There's a lot of indirect detection type
Yeah.
experiments looking for products of the things that dark matter does. But that's an open question.
So do you think, say, look forward, 5, 10 years, do you think we will have a
Well,
complete picture
I
that
hope
includes
so.
dark matter and dark
How
energy?
confident I am, I'm not sure. I think our best shot was when the LHC turned on, and when they did not see
Yeah.
anything, and when they went to their second run at higher energy, and they still didn't see anything. Um,
Mm.
it got a lot of people nervous. Actually, the value of the Higgs mass that they found, it's 125
Yeah.
GeV, so about 125 times heavier than the proton. That was certainly
Mm.
a viable. It was in the range that was expected. It was within the predicted range for the Higgs mass, but it was on the heavy side, and that meant that it might be hard for them to make all these other particles that were anticipated.
Mm. So either you need a different
Yeah, you might need
infrastructure
a much
to
bigger
get to the
accelerator,
energy,
and of course, then
or perhaps
that
yeah.
takes money. Primarily, it takes lots of money, and I'm not sure that right now we have the money, and it takes a lot of time.
Yeah.
So 5 years, that would be great.
Right.
It would be wonderful. Uh, I would not be betting that in 5 years that dark matter is discovered. I would love it.
Mm. There was some there was some talk about, Keith, some issue with the Hubble constant
Yeah, there is.
measurement
So there
showing
are all
different
sorts of
values, right?
tensions. Not everything. I maybe painted an over rosy
Yeah.
picture, but there are some tensions. The one
Mm.
that's getting the most attention right now is the Hubble parameter. So the Hubble parameter tells us how fast the universe is expanding, and from that you can infer, for example, the age of the universe. Um, and depending on how it's measured, whether it's from the microwave background or from looking at distant objects receding from us, you get slightly different values. And so it's measured,
Mm.
the units are maybe for some people funny units, but it's measured in kilometers per megaparsec per second. And so if you put something a certain distance away from us, it'll tell you how fast it's moving away from us. So from the universal expansion. And the numbers are like, some numbers are around 68, some numbers around 72. And now the question is, what are the error bars? Are they really in trouble with each other? And the estimates for those uncertainties are such that the people talk about 4 sigma, which would be unlikely but not impossible. Now I have to say that when I was a student, then there were different measurements of the Hubble parameter. Some were 50 plus or minus about 5, and others were about 100 plus or minus 5. That was a big problem. And then somewhat later, actually Wendy Friedman, who's now in Chicago, said, well, when I do it, I get about 75. And or between 70 and 75. And that number, the people that said 50 and the people that said 100, no way. But it turns out she was more or less on the right track, actually quite a bit on the right track. And so to me, this difference between 68 and 72, it's probably because of my personal history. Just remembering the arguments that people were making between 50 and 100, between 68 and 72, to me, those sound like those are almost the same number. That's
It's good enough.
Good. Yeah. And, I think, it could also be systematics that people are not, well understanding the uncertainties that they're getting, that the uncertainties may be a little bit larger, or the corrections, there aren't the appropriate corrections being made. But that, I think, could be sorted out within the next 5 years. So tensions like that. Then, of course, discrepancies are supposed to happen, right? Statistically, they should happen. Now, you shouldn't have too many 4 sigma ones, but, 2 sigma should happen,
and that totally
5% of the time.
Yeah. And I believe those numbers are from totally different.
One is from the microwave background,
methodologies,
which
too,
is then
right?
talking about a period, a few 100,000 years ago, and the other ones are coming from, sort of distant measurements, but much more like today.
Right. And so, in conclusion, Keith, let me ask you this: so, what are you most excited about?
Looking forward, resolution to the questions of dark matter, I think are, I'm a little pessimistic that it'll be within 5 years, but that's the thing that can be resolved sort of on the close scale horizon. I'd also be most excited if, when the LHC is running again, that really we do see some really distinct differences from what we call the standard model, that new particles are discovered. There's still certainly possibilities for that, and that's that to me would really shake things up and be very exciting to me. Some of the other questions. Let me add another one, and that has to do with the microwave background, and that has to do with it's seen in the polarization of the microwave background. I said that there were some observables that have proven, that are predicted by inflation and have been proven. One is the flatness of the universe, and the microwave background tells us the universe is extremely flat, spatially flat, I should say. The other tells us something about the anisotropy spectrum, how matter is distributed. And it makes a very, very distinct prediction for how that spectrum should look. And that's also been seen to extremely high precision, that this fits right in with the predictions, with the initial predictions of the microwave of inflation for the microwave background. Well, it makes another prediction. Some theories of inflation make another prediction that can be seen with the polarization of the microwave background. There's 2 different kinds of perturbation spectra in the microwave background. One's called tensor, one's called scalar, and the ratio of the 2 can be observed and is predicted. And that is now within the near horizon of future experiments, of microwave background experiments. And if they can actually see this ratio, this polarization that's predicted from theories of inflation, that would be also, I think, really, really phenomenal, and also tell us something about what type of inflation actually happened, what model of inflation might be the correct model, and really tell us something about what happened in the very, very early stages of the universe. So that's something probably more than anything else is doable in the near future, getting this polarization, this signal in the polarization of the microwave background.
And those experiments, I guess, are ongoing, right?
That's right. There are
one
ongoing experiments.
in the South
whether or
Pole,
not they'll have the sensitivity is not clear, but all the next generation of experiments that are being proposed will have that sensitivity, unless the number is really tiny. I mean, there are predictions which are saying it's really right around the corner. In fact, the original model of inflation, its prediction would tell you that it really is just around the corner, about a factor of 10 or 20 below their current sensitivity. So that's doable. If it's a factor of 1,000,000 times smaller, that's probably not doable. But a factor of 10 is certainly achievable.
Right. Right. Excellent. Yeah, this has been great, Keith.
Oh, sure.